Hello everyone, my name is Michael. Today we're going to take a look at some ransomware. Now today's sample, I want to actually take a look at the Keygen. So we're going to analyze how it generates the key that it's going to use to encrypt files and kind of find out how it protects it possibly. So we'll start out with a quick static analysis in PE Studio. So we'll confirm here it's an executable, maybe it has a GUI, it's 32-bit. Has low entropy, so it's probably not packed. Signature is actually an MASM, which is actually a compiler that's a little more advanced. Combines C and assembly, so possibly we're dealing with a little more an advanced actor behind this, so that's kind of interesting. Taking a look at the libraries, we'll confirm we have the advanced Windows 32 base API again. So that's going to tell us we're probably going to see some Microsoft CryptoAPI calls, which if we sort by name here, we can confirm. We have Crypt Acquire Context and Encrypt and Export Key and all that fun stuff. Let's take a look at the strings. And we have some strings with the ransom note. We have a decode.key file. That might be something interesting to keep a lookout for. We have our functions once again. On this one, we actually scroll over. We can see that's a string for Microsoft Enhanced Cryptographic Provider. We have another clue of it being the Crypto API. Looks like the ransom node actually mentions that decode.key, so that will be interesting to follow. And just some more garbage down here. So we're going to once again open this up in a disassembler. The one I use is IDA freeware. And we'll start out at the entry point here. This is where the malware actually starts executing once you run it. So we actually just have kind of one main function here. Let's go ahead and take a look into this one. And it looks like we're going to probably copy ourselves as notepad+++.exe. That's kind of interesting under the Windows directory. We got some stuff with the registry that I'm not too interested in. Okay, here we go. So let's start out at taking a look at the Crypt Acquire Context. This is once again going to be our setup for using the library. So we'll see the usual kind of the boilerplate I mentioned before, where you call it a couple of times to make sure you got the permissions right or different flags and such. In between videos here, I actually learned of a new function. Shout out to Malware Hunter team for teaching me this. If we actually take a look at the, like for instance, this flag here, I can actually right click on this and go to use standard symbolic constant. Bit of a mouthful there. But it actually shows me different constants from the Microsoft SDK that may apply for that value. Now, just knowing off of the Crypt Acquire context, most of those flags start with crypt underscore. So we can actually fill that in, and that's pretty cool. Let's see. So after our acquire context, we've got it in this provider here that we're probably going to use for all of our future functions here. We have a call to Crypt Import Key. So once again, this is going to probably import some type of a static key, likely asymmetric. Looks like we're going to be looking for 276 bytes or 114 decimal or hexadecimal. And the actual bytes that we're importing is this section here of PB data, which is looking like a Microsoft blob. So we have this RSA1, which is a public RSA key. I know that actually due to the format, if you read the documentation, the next 4 bytes is the size in hexadecimal, I believe little endian. So actually this is 800, which is 248 in hex or in decimal. We'll see that later once we go to actually maybe dump this while it's running. So that's interesting. So we'll take a look down here. We acquired different contexts for whatever reason. And we actually use it for, we use it for CryptGen Key. Now CryptGen Key is a new function here that we're going to look at the documentation for. This function generates a random cryptographic session key or a public-private key pair. So basically it's telling us it generates a cryptographically strong random key for either asymmetric or symmetric, but depending on what flags you give it, pretty much. It's pretty much kind of the same as Cryptgen random here, which is a function that fills a buffer with cryptographically random bytes. So cryptographically random bytes means we can't guess it. We can't like try to seed it and brute force the values. It usually uses some type of entropy from the system to make something cryptographically strong. So this already is an indicator that's probably a secure key that they're using. So we'll take a look at the syntax here. So we're going to pass it our provider, of course. We're going to tell it what algorithm we want to use, some flags, and then a handle to the key that we're going to get as a result of calling it. So once again, the algorithm ID, we're going to tell it, if it's going to be AES or DES or whatever. Let's see, the flags. Okay, so the flags is going to be where you tell it how big of a key, if it's asymmetric, basically, in the high bytes. Otherwise, you get your usual Crypt exportable is probably what we're going to see in this one. And let's take a look here. Yep. Number 1 DW flag is Crypt exportable. So we can take a look at the algorithm it uses. So 6610 should look familiar. But let's go ahead and go to this. And yep, we'll confirm it is AES 256. So with this function, we're going to generate a secure random AES 256 key. And we're going to dump it into this variable here, this ph key. Now, if we follow this down, we'll see we next use that variable in the Crypt Export Key function. So this function will actually export this key so we can turn it into something if we want to, use it in a different application or something. But in this case, it looks like we're going to export it as a blob type of 8, which I believe is a plain text blob. And we're going to export it to this variable, pb data. So this variable is going to actually hold our plain text key. We want to keep a look on that later. So we're going to export it. And the reason we do this is because the Cryptgen key, basically you get a handle to the key, and you can use this key to encrypt stuff with, but it's not going to give it to you in a form that you can read it yourself, so to say. It actually has to be exported to a blob type to actually use it in another application or just read it. So we'll see. So that gets exported. The plain text of it gets exported to this variable, which the next time we see that is being passed to Crypt Encrypt. So if we follow this key, so basically we're actually going to use the key that we had up further to encrypt the plain text blob of the cryptographic key that we generated here. So already at this point, it looks like they're generating a good key and they're securing it properly. So let's see here. So we destroy the key, we acquire context. Let me grab that variable again, LP string 2. So that encrypted key now is going to be written to our decode.key file. Once again, create file. We're going to create this file name. It's gonna write to that file. The set file pointer is just gonna set to the beginning, I believe. So okay, so that's gonna be that decode.key file that was in the ransom note. So, and also just to confirm, 100, we got 256 bytes. We're gonna write to the file. So at this point, just to kind of confirm what we're seeing here, I'm gonna go ahead and open this up in a debugger. Now the debugger I use is X64DBG. This is the 32-bit version, X32DBG. It's also a free tool. And a debugger is basically going to look kind of like the disassembler, but we're going to actually step through the assembly and actually run this and see what's going on in memory while it's happening. So we'll start off at just whatever memory, whatever's going on here. If we hit run one time, we're going to start at the entry point. So this is the beginning, that first function we saw on IDA. So what I'm actually going to want to do, I'm going to drill into, oops, I don't want to change that. I'm going to go back to IDA here, and let's find a good place we want to kind of set a breakpoint. So I'm going to set here, we're going to see this address, 4019BD. This is our offset into the executable. I'm going to use, in the command line down here, I'm going to use BP, which is breakpoint, 401, and that offset was 9BD. Hit enter, and we have a breakpoint set. We can go ahead and go to breakpoints here, double click here, and here we are at our familiar Crypt Import Key. So let's go ahead and we're going to hit run once, and we'll see our pointer is right here. This is where we're actually at. The executable is running right now, but we've paused it. So let's just double check in IDA. We probably want to look at this second variable here. We want to see that key. So that would be this one. I'm going to right click on that. We're going to go to follow and dump this address. And there we go. There's our RSA1. Once again, hexadecimal 114 bytes. Let's go ahead and copy that. Yep, well, hexadecimal 114 bytes. I'm going to go ahead and binary. I'm going to save that to a file here. Let's dump it to the desktop. We're going to call that just rsa.bin. So we can take a look at that over here. I'm going to use my blob analyzer. Import from the desktop rsa.bin. And here we can confirm that blob is a public key blob. It's an RSA key, 240 or 2048 key. So already here we can tell this is a public key that's going to encrypt, and we're not going to be able to break this key. This is not a weakness in the malware. So let's continue taking a look here. Get past that import. Okay, crypt acquire. All right, so now we're at the crypt gen key. Take a look back in IDA here just to confirm where we're at. Crypt gen key, we're going to generate our AES 256 key. And we can't actually, like I explained before, we can't actually view this PH key. It's just going to be a pointer to a key, basically in memory. That's not in a form we can really view it. So we can't really hook into where that function's called. So we're just going to skip over that. And we're going to come down to the Crypt Export Key. Now this is where we're going to want to look at what's being output from this. So if we come back to IDA, let's see, our LP string 2 is, we got the 080 going on, and then our variable that we want. So we got the 080. All right, so we have a variable here. Let's go to dump 2. Going to right click. Follow and dump value. So right now we're passing in a variable that already, just for whatever reason, has the executable path in the memory. But we're going to see when we step over that's going to get overwritten. So now our buffer has a cryptographic key blob. And we see the length of it here, I'm just assuming based on the zeros that it's 2C bytes hexadecimal. But we can actually go to the variable right above it, this other variable, 6C it looks like. Follow that in dump, go to the address, and that's the length parameter once again. If we look at PDW data length, that's how many bytes export key is telling us the buffer is. So we confirm we have that many bytes. Let's go ahead and binary save to file. So this is our AES key that was generated, and right now it's in plain text. It's a plain text blob. Once again, we can take a look at our blob analyzer here, aes.bin, and yep, we have a plain text key blob for AES 256. 32 bytes as needed for AES 256. Okay, very interesting. And then if we actually keep a look at this memory here, let's continue stepping through. We'll see that same buffer is going to get pushed onto the stack. And we're going to call crypt encrypt, and there goes our key. Now it's an encrypted mess. And we'll actually see, we could copy this. Once again, whoops, that many bytes, binary, save the file, desktop, let's do encrypted.bin. Now this is not a cryptographic blob, it's actually raw encrypted with AES, or I'm sorry, RSA. So if we actually, then we step through, we destroy the key. So this is what I would expect to get written to the decode.key file. Let's go ahead and step through. Now let's go ahead and go to that Windows folder. We can actually watch this be created. So we'll see, I typed in DE and there's no DE file here. Create file. There it is. Set the file pointer to 0. We're going to write 256 bytes because that's how many bytes are encrypted, or what the ciphertext size is. All right, close the handle. Now we got some text in here. Let's go ahead and confirm. Look in the hex editor, and yep, that looks familiar. Here's our encrypted key, and yep, it's the same as what we dumped out of memory here. So before we let this go rampant, I'm going to go ahead and copy these keys over my FTP here, because this one's going to get a little out of hand. Let's go ahead and copy those in a safe place. And let's go ahead and let this malware do what it wants to do. Just continue. And we'll see it closes everything. And it's doing something with the user account control. That's very interesting. It must be doing some override or something. So we'll see. Half the time I run this, it encrypts my entire desktop. So that's why I copied that as a precaution. Let's take a look here. Okay, it's encrypted some files. Here's our ransom note. Send us this file in order to do stuff, pay us money, all that garbage. We're not going to pay you anything. Let's take a look at our encrypted file here. Oh, now Windows is caught on to me. So we'll see, yep, this file looks like it's encrypted. It actually seems to have a bug. These 2 bytes I recognize are the plain text. So either it doesn't encrypt the whole file, or it's goofed up on how it does a buffer. Padding buffer, rather. So let's go ahead and see if we can confirm that we can decrypt this using that key that we pulled out of memory. So let's grab our AES key as a key blob. Tell it it's a blob. It detects that it's an AES key. Now they have something wrong with their padding, so I need to just do an arbitrary number here. And decrypt, and we'll see this FFD8 or D8FFEO is a JPEG. So we can actually kind of save that as decrypted.jpg. That's probably going to be corrupted since it's not very much data. I'm not sure if that's the entire header there, but if we take a look in a different the other hex editor here, we can actually see the ASCII of it. So, yep, this looks like we were able to decrypt it with the key that we pulled out of memory. So that kind of is a proof of concept as to what the ransomware is doing. Now, unfortunately, this sample is a ransomware known as LockCrypt 2.0. And they fixed all their flaws, rewrote all the code, as you can see, and it is secure. The only way that I was able to decrypt this file was because I cheated and I pulled the key from memory. So, unfortunately, once the malware has finished running, that key is as we saw, it's only in its encrypted format, or as a pointer, basically. So as soon as the malware executes and finishes, that key is gone. It's completely encrypted. It's in our Windows folder here as the decode.key. So like I said, the victim would send this to the criminals. They would decrypt it with their private key that matches our RSA key we pulled from memory here, whatever the private key for this is. They decrypt that encrypted key here, and it would become a raw blob that would decrypt to this. And then they'd give you a decryptor with this, and it would be able to decrypt all your files. So that has been a look into a Keygen using the Microsoft CryptoAPI. Thank you for watching, and please tune in for any other ransomware related videos that I can come up with. Thank you.